Okay, in this experiment we're going to measure the chemical kinetics of hydrogen peroxide decomposition. That means we'll take a little bit of a hydrogen peroxide solution, we'll add some iodine catalyst, and we'll see how fast the reaction goes. In order to independently check out iodine and peroxide, we'll measure their concentrations and vary them independently, see how they affect the rate. I'm going to show you a sample problem so that you can then apply it to the general problem. For any reaction of A plus B goes to products, we ignore the coefficients for determining the rate loss. So the rate is just equal to some constant, which we can figure out at the end, times the concentration of A, which is a reactant, times the concentration of B, which is the other reactant. And we use these exponents x and y. The reason we do that is because typically we find that doubling the concentration of A will either have no effect on the rate, a proportional effect on the rate, or an exponential effect on the rate. In other words, x can be 0, 1, or 2. I suppose it could be higher as well, but that's pretty rare. We can do the same thing for B. We keep A constant. All we do is change the concentration of B. It's logical to simply double it and see if it doubles the rate. If it does, then y equals 1. If it has no effect, y equals 0. If doubling it quadruples the rate, then y equals 2. You might be beginning to glean that the really key formula is that I'm going down here now, the change in the concentration factor, in other words, doubling the concentration, for example, times 2 the rate order will give us the rate factor. Let's say that a little more clearly. If we double the concentration and that doubles the rate, the order is 1. If we double the concentration, it has no effect on the rate, the order is 0. If we double the concentration and it quadruples the rate, the order is 2. I hope that's clear. Typically, you see a list of experiments, and in 3 experiments, that can be enough to determine the results of each of the reactants. Check out this one. Okay, we tripled the concentration of B, no change of A. Did it triple the rate? It did. It's first order with respect to B. In other words, 3 to the first equals 3. Let's take a look at trials. Oh, and by the way, for trials 1 and 2, it's really important to note that they didn't mess with A. See how that didn't change? That would be difficult to determine any results at all if they didn't do that. Okay, take a look at the other trials that matter. Let's take a look. Where did they keep B constant? It looks like trials 1 and 3. That's where B is constant. What did they do to A? Well, it might have been nice if they doubled it, but they didn't, so we can deal with that. But they multiplied it by 1.5, didn't they? 1.15 plus half of that, which is 0.75, equals 0.225. So it's a 1.5 times concentration factor. Did it make it go 1.5 times faster? That would have been 12, but no, it's 18. So we have to do a little math there. Well, 1.5 is the concentration factor, 2.25 is the rate factor, and in fact 1.5 squared equals 2.25. This reaction is second order with respect to A. So it's very sensitive to the concentration of A. You increase that a little bit, it'll increase the rate a lot. If you wanted to make the reaction go faster, that would be the one to double. Okay, so overall we can say that the rate is equal to some constant times the concentration of A to the second order times the concentration of B to the first order. More sensitive to A than B. But how do we solve for K? Easy. Just pick any trial you want, typically the first one, and you got everything except K. So what was the rate for experiment 1? 8 times 10 to the minus 4th molar per second, so plug that in. It's equal to that rate constant times the 2 concentrations, 0.150 and 0.3. Solve for K and you get 0.118 molar squared per second, so we have the entire rate law, which is the purpose of this experiment. And that would be that for the sample problem. Apply that to the hydrogen peroxide decomposition. Okay. Our real problem is that we're decomposing hydrogen peroxide, so our only reactant is the peroxide. We do use an iodine catalyst, so we'll also consider the effect of that. You might be able to guess what the effect of that might be since it's a catalyst. Okay, so The rate law will be some constant times the concentration of peroxide to the x times the concentration of iodide, our other reactant, to the y. We're going to set it up just like this in the experiment and then solve it just like we did for this one to find a final rate law. So we'll find K, X, and Y by monitoring the pressure of oxygen. That's the product. So the more pressure you've got, the faster the reaction must be occurring. In the pre-lab, we'll do the molarity of a 3% hydrogen peroxide solution, assuming the solution is 1 gram per mil. I'm going to let you do that on your own. We'll evaluate the safety dangers of this experiment. In the quiz you take at the beginning of class, I expect you to give me a nice analysis of the safety factors for this lab. And then, as usual, we'll fire up Logger Pro, experiment 12 in this case, and set up the gas pressure assembly as shown here. There's the gas pressure assembly. Note this is a closed system, which is potentially dangerous, but at the very worst, what would happen is this rubber stopper would just pop off. Okay. Add the potassium iodide solution, that should say water, and stir it up with a stir bar. It's not sealed yet. Now when you're ready to go, you add that peroxide, the reaction begins, so immediately seal it up and measure the pressure as described in the Logger Pro part of the experiment, which I never provide in detail, just do what it says. We'll do 2 more experiments, and notice that we're doing 3 experiments in the sample problem. And in each case, let's hope that they intelligently vary the potassium iodide concentration as well as the hydrogen peroxide concentration. Print all 3 graphs and perform the following calculations. A, B, C, D, E, F. It looks like 6 calculations. I'd like to see them in your lab report, please. The pre-lab concentration of peroxide in terms of molarity. The initial peroxide molarity. In other words, just because you have a 3% solution to begin with, we'll be diluting it with some things, and I'll show you a sample example of that. And that's the real initial molarity. Same thing for potassium iodide. I'm about to show you a sample calculation below. The order of reaction for hydrogen peroxide, just like you did for over here. The order of reaction, how sensitive is it to iodide? And please give me the nearest whole numbers. I'll show you a sample calculation there. And K for each experiment. So we'll do it for this one, this one, this one. For the year, we just picked any one, but why don't you do all 3, please, and then take the average, and then answer the post-lab questions. Okay, 2 sample calculations. First, this initial molarity thing. For example, if you're using potassium iodide, which you will be, and the bottle says it's 0.1 molar, that doesn't mean that it's 0.1 molar when you're performing the experiment. In this particular example, we have 10 milliliters of the 0.1 molar, but we also added 15 mils of water and 5 mils of peroxide. So the total volume of the solution is now not 10 mils, but it's 30. It sounds like it's going to be 1/3 of that initial molarity. But just to make sure, do an M1V1 equals M2V2 calculation, and here's what it would look like. 0.1 molar of 10 mLs should be equal to the new molarity at 30 mLs. Okay, the other calculation, which I want to show you an example of, is finding the rate order, because it's not always, see how 1.5 to the second order equals 2.25? It's not always going to be absolutely beautiful that you're going to get whole numbers. Find out what the exponent is and then round to the nearest whole number. It's probably good if it's close to 1. That's a good sign. So suppose that the concentration factor was you tripled it. Now that to the reaction order will equal whatever the rate factor was. And suppose the rate increased not by 9 times and not by 3 times, but by 7.37 times. Solve for x. Take the log of both sides and divide. So in this case, the log of 7.370 divided by the log of 3.00 will be your rate order. And don't be surprised if it's, not a perfectly whole number. In this case, with 1.818, round it to 2. I'd rather not see any rate orders that are non-whole numbers. Use whole numbers, please, for the rate. This is the chemical kinetics of hydrogen peroxide decomposition experiment.